Jnanam paramam dheyam. Knowledge is supreme.
In the context of quantum physics, let me explain and motivate you how you can see a Fourier transform. Okay. So, the way you do, if you have a de Broglie wave, okay, wave of wavelength lambda, which means you can write wave number as 2 pi by lambda, then you could write the wave function for this de Broglie wave as a sin kx. This I am sure all of you have seen. No? Yes or no? It's like an electromagnetic wave with a specific wavelength. You could write this. If you have time dependence, you can put a kx minus omega t. Let me just take psi of x. And you can do superposition of two waves. You can have psi 1 as k1 and you can have psi 2 of x as some other amplitude maybe or same amplitude, sin k2, let me take k2 as k1 plus delta k x. So, what will this superposition be? It will give you a new superposed wave which you can write it as psi 1 of x plus psi 2 of x, which is the superposed state. You can do that. So, when you have only one de Broglie wave, it has a definite wavelength. If you start adding one more wave, then you will start seeing that there will be some kind of a superposed state with not definite wavelength, but with some width which is proportional to your delta k, right. We have done this as one of the assignment problems. If you superpose many of them, what is that called? The superposed wave function or the superposed wave. I have just done two of them, two de Broglie wave with definite wavelengths. But if I have many of them, so let us take k1 plus 2 delta k, k1 plus 3 delta k and so on. What are you supposed to get? Wave packet, right? Wave packet is a superposition of many de Broglie waves, okay. You agree? Of different, let us take of k lying between k1 to k2 in steps of delta k, k1 plus delta k. So, k, the list of k's you can have is k1 plus delta k dot dot dot, you go on till k2. So, that is a wave packet, superposition of all possible de Broglie waves, and this wave packet when we start doing, what happens? You lose a specific wavelength for the wave packet, right. De Broglie wave has a specific wavelength, a single de Broglie wave has a specific wavelength, wave number or wavelength. But if you start superposing many de Broglie waves, the information about the wavelength is gone. You all agree? But what happens? Wave packet is very close to particle, which means you will start seeing the amplitude to be a maximum in really. So, if we put it pictorially for you, so a de Broglie wave will be like this, keeps going, let me not stop it, it keeps going, with a definite wavelength, a single de Broglie. But how does the superposed wave going to be? It's going to have some kind of a peak and then the amplitudes dampens down, right? Something like this. I'm not very good at drawing. Something again it goes, you know, or it may just damp down also. Not really drawing to scale, but you can do this. But then the wavelength for such a, this is what we call it as a superposition of all possible de Broglie waves, which will give you a wave packet. Suppose it damps down everywhere and there are peaks only in this region. Okay, let's say it damps down everywhere. Then this is the region in which you have maximum amplitude for the superposed psi of x versus x, right. So what does that tell you? The probability of finding the particle is maximum only in the small region, which means you are able to localize. It's not here when I want to find where is the particle. It can be anywhere because there is a periodicity. At periodicity will go, it will damp down when you take a superposed wave. So you get a localization here for the wave packet, whereas here you get a specific wavelength. Here you don't get a specific wavelength. You all agree? So specific wavelength means what? By de Broglie's hypothesis, specific P. So which means momentum is well defined, but you cannot localize the particle here if it is a single de Broglie wave. But if it is a superposition of all possible waves, then the amplitude is maximum in a small short region. You can make it even more shorter by taking all possible wavelengths from wave numbers from minus infinity to plus infinity. Okay, so you can take that. If you do that, then it can get more and more, this region which I can call it as a delta x, this region could get more and more shorter, and you can actually say that this particle is localized here, but its momentum is not. Its position is well defined, but momentum is not there. Correct? So this is the main theme in which you can also see superposition as Fourier transform. Okay. So for a single wave, I wrote psi of x as a sin kx. If I want to write the wave packet and let's take k to be going from minus infinity to plus infinity in steps which are very, very small, delta k is really small. Formally you could write it as summation over n, a sin k plus n delta k. Okay. Can take steps from 1 to infinity or something. Could do this. But if I want to take delta k to be really very, very small, what can I do? I can put an integration. Right? You agree? This summation is in discrete steps of the wave number, k shifted by k plus. If you have finite 2 de Broglie waves to superpose with k1 and k2, you can do the summation. But if I say that I want to take all the de Broglie waves with a continuum wave number, then what is the next one you will do? You have to put it to be a integration. You all agree with that, right? So how will you do the integration? So psi of x, formally I can write it as integral over dk. Then you can have, even this amplitude could be a function of k, kn, if you want to keep a subscript for this whole thing I could have called it as kn. So you could have an amplitude which is dependent on k, and you can have a sin kx. Going from some limit, if you want, you can go from minus infinity to plus infinity. So this is what we have been doing, but we are doing a little bit more. We wanted to keep the sin kx formally may not be the general, you will have a cos kx also. So I said we could try and rewrite this as e to the power of ikx and ak. So what is ak to be interpreted here? Suppose I replace this by e to the ikx. So let me rewrite it again here. Some normalization, we don't need to worry about the normalization. This is nothing but your familiar Fourier transform, where the Fourier transform A of k is the Fourier transform of psi of x. In the electromagnetic waves, you know what is superposition. You do look at beats, you do look at stationary waves, all these things I am sure you have done it. But it is not very different from the de Broglie wave. De Broglie wave is a matter wave. Only thing is, because it is a matter wave, we always think that we should be able to locate the particle, right. So, to locate a particle and to look at the particle velocity, which is the wave packet velocity, you need to find out d omega by dk, right. So, these things requires you to look at a wave packet, and the wave packet, if you have superposition of all possible waves, and suppose you denote this wave by an exponential ikx, this is nothing but your Fourier transform. What will be the inverse Fourier transform is the next question you can ask. So this one I told you, in the function space basis functions, these are like phi n of x or phi k of x. Okay. If it was a discrete sum, suppose you did a discrete sum, how will you find out what is a of k? When we had psi of x as summation over n Cn phi n of x, what did you do? Cn was, you integrate both sides with phi n star of x, psi of x. Integration is over dx. This is what you did. Now what will you do here? You have to take the phi k star of x on this side, and that will give you the coefficient a of k. So what will a of k be? A of k will be integral over dk, sorry d, it won't be dk, it is dx. This is what you are going to redo in a continuum. Integral over dx, phi k star of x is what? E to the power of minus ikx. How the minus ikx comes also you can see. This is the inverse Fourier transform times psi of x. Take the free particle will have energy to be h cross squared k squared over 2m, which is p squared over 2m. You can replace your k as 2me by h cross, this k, and you can start doing that problem where it is involving Fourier transform, go from the k space to the x space. Now you can go back and look at it, it's nothing but it's using this concept of Fourier transform and inverse Fourier transform, which you can also visually see it as a wave packet, which is a superposition of de Broglie waves. This is why the continuum comes. This discretized thing which we do is only when there is a periodicity. So this thing which I wrote here, this will have some condition like psi of x equal to psi of x plus r. In continuum you don't have that condition. So that is why you will start seeing phi n of x, which you can write it as sin kn of x. So you can write phi n of x as sin kn of x, for example. X equal to x plus r, it should be same, will force kn to be 2n pi by r. You agree? So this is why the periodicity condition discretizes your momentum or the wave vector. Okay. So, if you put a particle on a circle of perimeter, let us say 2 pi r, when you finish 2 pi r and you come back, it is the same point. You can't have two different wave functions at the same point. If it is x and x plus 2 pi r, it better be same. So, that condition, single valuedness of some periodic functions will allow your wave vector to be discretized. But if it is a free particle going from minus infinity to plus infinity, there is no periodicity on k. So, that will force you to do this integration. So, you should know when to use discrete, when there is a periodic function, or you put the particle constrained on some region with some boundary conditions like this. Otherwise, you will have k to be a continuum, and k is a continuum means you have to put an integration, and there is no meaning in talking about summation. So, that is about the Fourier transform on inverse Fourier transform. So, let me get on to today's lecture, where I want to formally introduce postulates of quantum mechanics. Okay. Okay, so before I go, what all we have done? Square integrable functions, which we denoted as L2 of a comma b, this we have done. Then I have also introduced for you square summable sequence, collection of square summable sequence, and that we denoted by a little L2. Okay. A collections of the set phi n, each one, this set is a sequence, and that we denoted by little L2. Okay, and we also seen that in such a L2 space you can write an arbitrary state by inserting this parenthesis, which is a unit operator. It is just a unit operator operating on that state, but you can reinterpret it as looking at this inner product of the state as a probability amplitude, which we denote it as Cn. And then the state should have a finite norm, any arbitrary state, forces that these Cn coefficients should satisfy this property. This is a condition for square summable sequences. Okay, so slowly we need to get, many times you will hear this word that this vector space is always called as a Hilbert space. So just to spend few minutes on what is the definition of a Hilbert space, and all the quantum mechanics problems assumes that we work in a special vector space, linear vector space, which is called as a Hilbert space. So first of all, the square summable sequence is a Cauchy sequence if it obeys certain properties. So you need to take n and m very large, and if you take the difference between these two vectors, take the norm of those two vectors, it should tend to 0. Similarly, in that sequence, when n is very large, it goes to some finite value, and then we call the state phi to which it goes, that is a limit vector. So many times we are going to assume that whatever linear vector space we are looking at is actually a vector space which has this limit vector, and we call such a vector space, at least technically it is called as a complete linear vector space. So these are some of those definitions which goes into the formal definitions, but many of the times we say we work in Hilbert space, but I thought at least as a quantum mechanics course we should know that when do you call it as a complete vector space, if the limit vector is included in the linear vector space, it is called as a complete vector space. When do you call it as a Hilbert space? Not all linear vector space you should have an inner product defined. There can be spaces where you don't have an inner product, like you really don't need to have an inner product. Like if you take the Schrodinger equation, you find solutions, right? Or any arbitrary equations, you find a set of solutions. Superposition is also a solution, but you cannot find what is the dual solutions to them. So some of them may not even attribute thinking about inner products. If you have the inner product also defined, then this complete vector space is called as a Hilbert space. And in most of the textbooks or most of the literature, they put this curly edge. So, we are essentially doing linear vector space, but some of these things are assumed, that your linear vector space with this limiting vector in that sequence, in a finite summable sequence, is also included, and you have an inner product definition in that vector space. That is why this whole thing together is what we call it as a Hilbert space. This is just for the definition, that why we call it as a Hilbert space. Okay, so we also briefly went through what is a operator for observables in the last lecture. So, I just thought you should also know what is the definition in this. These operators operate on vectors in the Hilbert space now, and these operators are called linear operators if it satisfies that if you take a linear combination of two states and have an operator A, then you can separate it out. So, this is one of the properties. The second property is that if there is a complex scalar multiplying psi, you can take the operator to operate on the state psi and you can ring the complex number. And you can also have sum of two operators on an arbitrary state can be written as operator on each state summed up. If you have two operators, product earlier was the sum. If you have a product, when will this be equal? Only when AB is same as BA. Okay. So, in general, two operators AB may not be same as BA. So, in general, AB operator on psi will give you a different answer compared to BA operator on psi. So, the order matters in quantum mechanics. All the operators when I write, I have to be very careful with the order. Now, for example, if you have a P cross L, okay, you can have an operator like this. You can also have something like R dot P. Classically, you are allowed to do this. R dot P is same as P dot R. But quantum mechanically, R dot P operators operating on a state psi, is it same? Don't take it as unit vector, some R dot P. Is it same? It's not same as P dot R on psi. What do you have to do if I want to, what is this called? If I have a unit vector R by mod R, lets me put it. If I have a unit vector, R vector dotted with. If I have a unit vector, what is this operator? This is the radial component of your momentum. So, radial component of the momentum, whether you write it as R dot P, this one, or P dot R, it didn't matter in classical mechanics. But in quantum mechanics, we have to be careful. How do you make it careful? I don't want this distinction on PR, but here I see the order matters. I have to do it very cleverly. How do I do that? Try to take a symmetric combination. For this case, you can take R operator P plus PR divided by 2. So, this is also your PR in classical mechanics. Why positive and not negative? If I put a negative, what will happen? Becomes 0 in classical mechanics. What about here? In classical mechanics, how many of you have seen Runge-Lenz vector? That has this P cross L, right? So, that is Runge-Lenz vector component. Actually, there is a 1 over R, right? K by K R vector by R maybe. This is a Runge-Lenz vector. How will you do the quantum mechanic combination for this piece? Will you take a plus sign or a minus sign? This is same as minus of L cross P in classical mechanics. How do you do it? Quantum mechanics. So, quantum mechanics operator, P operator should be this. You have to symmetrize for a dot B operator. But if there is an A cross B operator, what will it be? You need to take, you agree? So, this is what we need to also remember whenever we do quantum mechanics. You can't just take your observable, whatever is your differential operator, but if there are more operators, you need to make sure if you want to make contact with some physical reality, should I have to symmetrize or should I have to anti-symmetrize? So, that is why I was saying in general, the two operators, in classical mechanics you could have said R dot P is same as P dot R, but I cannot do that here. Okay, and this also we saw in the last lecture. If you have an A operator operating on an arbitrary state phi, it gives you a new state psi. Then in the dual vector space, you need to replace it by the complex conjugate and transpose if it is a matrix representation, or we call this as a adjoint operator, A dagger, and that gives you the new state. So, A dagger is what we call it as a conjugate or the adjoint of A. Clear? Kind of summarizing whatever you have seen in the last lecture.